When you see one of those jaw-dropping, vibrant pictures from deep space, have you ever stopped and thought, how do we actually know what's happening in there? I mean, the universe is just mind-bogglingly huge. Its most epic events are millions of light years away. So how on earth do we study them? Well, today we're diving into the amazing science of how we bring the cosmos right down here into the lab.
Okay, just look at this. It's a stellar nursery, a place where new suns are literally being born in this breathtaking swirl of gas and dust. It's just gorgeous, right? Telescopes like James Webb give us these incredible cosmic portraits, but they also present a huge problem. We can't just, send a probe into the heart of an exploding star. We can't time travel to see a planet being born. So how do we actually test our ideas about how all this really works?
Well, the answer is just absolutely brilliant. If you can't go to the cosmos, you bring the cosmos to you. And that's exactly what the field of laboratory astrophysics is all about. Think about it. Instead of just sitting around passively waiting for the universe to send us some clues, scientists are actively recreating the most extreme conditions you can imagine. We're talking crushing pressures, insane temperatures, the perfect vacuum of space, all of it, right here in a controlled lab. This is how we go from just looking at pretty pictures to truly understanding what's going on. So let's dive in. We're going to start in one of the coldest places in the entire universe, those vast, dark molecular clouds just floating between the stars. To us, they look like nothing, just empty space. But they're not empty at all. They're actually these giant cosmic chemical factories where the very building blocks of planets, and maybe even life, get their start. So the big question is, how in the world do you study chemistry when it's happening in a near-perfect vacuum? Turns out, you follow a recipe, a sort of cosmic cookbook. In labs like Surfraside, scientists start by creating this ultra-high vacuum. First step, they take a tiny surface. This is our stand-in for a tiny grain of interstellar dust. And they cool it down to an almost impossibly low temperature. Step 2, they spray simple gases, things like water and carbon monoxide, right onto it. This creates a thin layer of ice. And for the grand finale, they blast it with UV light, just like the radiation from a nearby star. And then they watch to see what new, complex molecules pop into existence. This is how we figured out that things like sugars, actual sugars, can form out there in the cold of deep space. How cool is that? And look, when I say cold, I'm not kidding around. We're talking minus 263 degrees Celsius. That is just a few degrees shy of absolute zero, the theoretical point where all atomic motion just stops. The level of precision it takes to create and maintain that kind of environment, it's honestly just astounding. All right, let's do a complete 180. From the absolute coldest, we're now going to the absolute hottest, most violent events the universe has to offer, supernovas. I mean, these stellar explosions are so ridiculously powerful, they can briefly outshine their entire home galaxy. So to get a handle on that kind of raw, cosmic power, scientists had to figure out a way to study it without, getting vaporized. So what do? You build a tiny star, and then you make it explode. It sounds like science fiction, but at places like the National Ignition Facility, they do exactly that. They take some of the most powerful lasers on the planet and focus them all on a teeny tiny pellet of matter smaller than a pinhead. And in literally a fraction of a second, that pellet is heated to millions of degrees. It creates this massive shockwave that perfectly mimics the physics of a real supernova. And by doing this, we can study how that superheated stuff, it's called plasma, expands and creates the wild magnetic fields we see in the leftovers of real stellar explosions. Okay, let's bring it a little closer to home now. We are sending these incredibly sophisticated and expensive rovers to other worlds, like Mars. And the dream, of course, is to one day send people. But before we do any of that, we have to be 100% sure that our gear, our technology can actually survive in that brutal alien environment. So, what's the solution? You build a little piece of Mars right here on Earth. And this is what that looks like. Just take a look at the comparison. On the left, you've got the real deal, the actual conditions on Mars. On the right, that's what they've created inside the Pascal simulation chamber. And as you can see, it's pretty much a perfect match. They recreate the whole shebang. The thin CO2 atmosphere, the crazy low pressure, the intense UV radiation, the dust, everything. This lets engineers test all their gear, from rover wheels to life support systems, for months or even years, so they can iron out all the bugs before we launch.
You know, the uses for this kind of science are just so incredibly diverse, and they lead to some discoveries that are, frankly, pretty weird and wonderful. So, for this next section, let's do a little highlight reel of some of the most fascinating, surprising things we've learned from these cosmic labs. All right, first up, get this. Did you know we actually make diamonds to understand what's going on inside Jupiter? Yeah, it sounds crazy, but this is a real thing. It's called a diamond Anvil cell. And what scientists do is they take two absolutely flawless diamonds and press them tip to tip. And right in between, they squeeze a tiny sample of hydrogen. The pressure gets so immense, we're talking millions of times the atmospheric pressure here on Earth, that it's thought to literally crush the hydrogen atoms so tight that their electrons can just roam free, kind of like in a metal. And this weird, bizarre state of matter, metallic hydrogen, is our best guess for what generates Jupiter's ridiculously powerful magnetic field. Okay, next one for you. Did you know we can create stardust whenever we want? It's true. Scientists can basically burn specific gas mixtures to create tiny little soot particles. And these particles perfectly match the chemical fingerprints of the dust that telescopes see swirling around distant dying stars. So they create the dust in the lab, they analyze its signature, and then they compare that signature to what they're seeing light years away. If it's a match, bam, we know exactly what that stardust is made of. And how about this one? Did you know that to hunt for dark matter, this mysterious stuff that makes up most of the universe, we have to go deep underground? It seems backward, right? To find something from space, you go underground. But experiments like Xenon X are buried under a mountain for a really good reason. All that rock shields the detector from all the other cosmic radiation that's constantly bombarding Earth. So deep down there is this massive tank of super pure liquid xenon, and scientists are just waiting. They're hoping that a single dark matter particle, a WIMP, will eventually drift through the mountain and bump into one xenon atom. If it does, it'll create a teeny tiny flash of light, and that would be the first direct proof that this stuff is even real. It's an incredible test of patience. So, okay, we've talked about creating stardust, forging many supernovas, building a slice of Mars, all these amazing experiments. But the thing is, none of them happened in a vacuum, pun intended. They're all a critical piece of a much bigger puzzle, a powerful cycle of discovery. And this is how that cycle works. It's a three-step dance, really. Step one is observation. A telescope like the James Webb sees something weird out there, and it raises a question. Step two is theory. Scientists build these supercomputer models to try and explain what they're seeing. But here's the key. A model is just an idea. That brings us to the crucial final step, the test. The lab experiment is the ultimate reality check. It's where we find out if the theory is actually possible in the real world. It either confirms our ideas or sends us right back to the drawing board. It's this constant, powerful feedback loop. And honestly, that really gets to the heart of why this is all so exciting. It's a fundamental change in how we do astronomy. For centuries, we were just passive observers, right? Just looking up at the sky. But not anymore. With these incredible labs, we've become active participants. We get to ask the universe our own questions on our own terms. When you think about it, by recreating supernovas and newborn stars and the cores of giant planets, we're basically putting the universe's history in a bottle. It's just an incredible testament to human curiosity and ingenuity. And that leaves us with one last big thought to chew on. If we're getting this good at recreating the past, what are we going to have to build to start predicting its future?